So why is Belmont's Crackingstone uranium project an excellent prospect for the discovery of a major uranium deposit? Well, let's first start with faults. Nearly all uranium deposits in the Athabaska Basin are closely associated with fault systems, which play a major role in the ore-forming process by providing a conduit for hydrothermal fluids. These fluids can transport dissolved uranium from deep within the Earth's crust to locations where it can precipitate and form mineral deposits. Crackingstone has 4 major faults crossing the property. In the Athabaska Basin, uranium deposits are often associated with reducing conditions provided by graphite. When uranium-bearing oxidized fluids interact with graphite-rich fault zones, the uranium is reduced and precipitates out of solution, forming high-grade mineral deposits. As graphite is an excellent conductor of electricity, graphite conductors can be detected by electromagnetic or EM surveys. Crackingstone EM survey has delineated 3 primary graphite-rich fault zones, or structurally controlled graphitic corridors. Rock sampling on the Crackingstone property has returned some very notable high-grade uranium samples. These high-grade samples are associated with the graphite structural corridors. A 2008, 3,000-meter, 20-hole drill program tested an EM conductor in the northeast area of the property. All drill holes intercepted uranium mineralization over the 1.8-kilometer zone. Drill hole C14 intercepted 0.5 meters at 2.08% uranium within 0.9 meters at 1.18% uranium. A radiometric survey, or as it's also referred to as gamma-ray spectrometry, is a geophysical process used to estimate the concentrations of uranium at the Earth's surface by measuring the heat produced during radioactive decay of uranium above the ground from low-flying aircraft or helicopters. A number of radiometric uranium anomalies appear from the survey, which are coincident with the structural controlled graphitic mineralized corridors. Additionally, several of the anomalies coincide with high-grade uranium samples, increasing the likelihood that other anomalies could also yield high-grade uranium upon further sampling. With the additional radiometric data, Belmont reviewed the 2008 drilling results and found that, besides the 1.8-kilometer zone of uranium mineralization, the drilling also intercepted a 1.8-kilometer zone of hematite. Hematite is a type of alteration often associated with uranium, and its presence in alteration zones indicates uranium precipitation during the hydrothermal event. Of even more importance was the extensive amount of pegmatite intercepted across the entire 1.8-kilometer zone. In the Athabaska Basin, pegmatite is often associated with uranium mineralization. The revised exploration model now considers this alteration zone to potentially be a mineralized halo surrounding a high-grade uranium deposit. This area, known as the number 7 zone, named after the nearby number 7 adit, where 11 tons of 2.3% uranium was mined, has now become a high-priority drill target for the upcoming 2024 drill program. In addition to the number 7 zone, 3 other areas have been selected as initial high-priority drill targets. So why is Belmont's Crackingstone uranium project an excellent prospect for the discovery of a major uranium deposit? Because our exploration data says so.